So F equal BQV sine theta. So this is the magnetic force for charged particles moving in a magnetic field. And of course, you would have met this in module 3 as well. Because in module 3, what happens when you have alpha, beta, and gamma particles, we say they are affected by a magnetic field. When we say affected, we mean that there is a force acting on them when they pass through a magnetic field. So your alpha particles were positively charged. So if you have a magnetic field, what we're saying is that once you pass charged particles in a magnetic field, they are going to be deflected. So if you have an alpha particle, which is a helium-2 plus, all right, which you did in module 3, moving through a magnetic field, all right, what will happen is that the alpha particle will bend in that direction in the magnetic field. If you have beta particles, which is a negative electron, it will bend in the opposite direction. So what this is telling us is that when charges move in a magnetic field, there is a force, all right? So what happens now is that we can calculate the size of this force, all right? So even in CXA, you talk about deflection of charged particles in a magnetic field. So the particles were moving straight. So once they start to bend and curve like this, you know that a force is acting. So F is equal to BQV sine theta. So F is equal to the force measured in newtons, B, magnetic flux density measured in Tesla, and Q stands for charge measured in coulombs. All right. V is the velocity, and of course, theta is the angle. And theta is the angle between the velocity of these charged particles and the magnetic field. All right, and of course, that is normally given. So theta, the angle between the velocity of charged particles and the magnetic field, and that is illustrated by the diagram here. So if I want to calculate the force on a charged particle in a magnetic field, I just need to know the velocity of the charged particles. I need to know the charge itself, the magnetic flux density, and of course, the angle theta. So once I have that, I'm in business. All right, so that's the first thing first. So when charges move in a magnetic field, they're going to experience a force. Now, this is very, very important, as this is classic physics. What's happening now, last week, and then 3 weeks prior, there was a breakthrough. There was a breakthrough in nuclear fusion. Now, nuclear fusion is fusing atoms together, hydrogen and hydrogen to form helium. All right, so you'd have probably seen this as well. So that is what nuclear, that is what that is. All right, so let me just, all right, so hydrogen plus hydrogen to form helium eventually. This is what nuclear fusion is all about. And of course, this is also done in module 3, where you have small light particles can fuse together to form a bigger atom that is more stable. And of course, there's an enormous amount of energy. Now, this energy, all right, was captured a few weeks ago. And of course, it's creating a new wave. Because if they get this right, it requires millions of joules of energy as the input. But what they're saying is that millions of joules of energy goes in, but you get trillions and trillions of joules of energy out. All right. So it can be cost effective. But the important thing why I'm mentioning this is because this reaction reached millions of degrees Celsius. All right. So the temperature is very, 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 very high. All right. And you heard me right? The temperatures they were measuring was in the millions of degrees. So this experiment could not be done in a container. So what they did, they have to do this in empty space. They have to do this in the space around. All right. And to capture the particles in that empty space, they have to use a magnetic field. So, all right. So the magnetic fields were able to trap the charged particles. And of course, the reaction occurred in space, creating a lot of heat. So it was like creating a sun on Earth. All right. And what they did was to use a magnetic field. So this formula, F equal BQV sine theta, all right, was the formula that was at hand in keeping these charged particles in a magnetic field. Because when you have charged particles flowing in a magnetic field, what's going to happen? It's going to spiral. Those charged particles are going to start moving in a circle. So once the magnetic field is present, then the charges will be prisoners to that circle, prisoners to that orbit. It will never get off that orbit. So it's a spiral and spiral and spiral and spiral like this, moving in a circular fashion. Just the same way, the Earth moving around the sun is a prisoner to this orbit. It never gets off. 1 year passes, billions of years passes, trillions of years may pass, and of course it doesn't get off. So that's the importance of magnetism. So in this experiment, the magnetic force was used to do the nuclear fusion experiment that can create a lot of heat energy. And of course, this heat can boil water, and then the steam from the water can spin a turbine. And when that happens, then a generator is activated and you get electricity. All right, so that's the idea. So that is what they have been up to, and there is a breakthrough. All right, so there's a breakthrough, and of course, they're looking to do further work. And so if this comes to market, then no, this is something that can really sustain the Earth's energy. All right, so that's for that. All right, so that's for that. All right, so for this is the formula that we'll use. So once I have charges moving in a magnetic field, those charges will experience a force. And of course, we're going to still apply Fleming's left-hand rule. All right, so when you had a charge, all right, so a charge moving, so this is a negative electron that's moving, all right, upwards in a magnetic field pointing into the board. You can use Fleming's left-hand rule to predict the direction in which this electron will bend. All right, so if I use Fleming's left-hand rule, so remember, if I use Fleming's left-hand rule, I can turn on the camera for a bit. All right, so if I use Fleming's left-hand rule, what will happen is that the electron will be moving upwards. All right, so my middle finger should point in the direction of the conventional current, or it should point in the direction in which positive charges move. And of course, you'd have done this in module 3 as well. So my middle finger should be pointing downwards. If electrons are moving up, then it means that positive charges would have been moving in the opposite direction, or conventional current is moving opposite to electron flow. So my middle finger is down. My pointer finger is pointing in because the magnetic field is pointing into the board. And my thumb now is pointing to the right, as indicated by the blue arrow. So the electrons will be deflected to the right. All right, that's applying Fleming's left-hand rule. All right, so that's the idea. So applying Fleming's left-hand rule, we can predict the direction of the force. So for this example, you have a charge electron of 1.6 times 10 to the negative 19 coulombs. And this charged electron was moving in a magnetic field as shown. The strength of the magnetic field was 0.1 Teslas. The velocity of the electron was 10 to the 6 meters per second. And of course, the angle given was theta. All right, so you have an electron. This electron was moving at a velocity of 10 to the 6 meters per second. It had a charge. Of course, the charge on the electron is 1.6 times 10 to the negative 19 coulombs. And the magnetic flux density is 0.1 Teslas. And of course, what they gave us was the electron right now. The velocity of the electron is perpendicular to the magnetic field, as shown on this diagram as well, because the magnetic field is pointing into the board. And of course, the electron is moving on the plane of the board or the screen, and so that's perpendicular. So theta is 90 degrees. So given this information, since I know B, and I know V, and I know Q, I can calculate, all right, the force acting on the electron using the formula F is equal to BQV sine theta. B is 0.1 Tesla, so I'm going to put 0.1 here. The velocity is, all right, is 10 to the 6 meters per second. So I have that in the multiplication as well. The charge on the electron Q is 1.6 times 10 to the negative 19 coulombs. All right. And of course, we have sine of 90 is 1, but we just put it for practice purposes. So it is BQV sine theta. And of course, we will calculate the force. And the force was found to be some number. All right, so multiply these three numbers. Okay, so the force was found to be 1.6 times 10 to the negative 14 newtons. All right, so we multiply these three numbers. Given that the mass of the electron, all right, so this number you'll always get on the paper. Given that the mass of the electron is 9.11 times 10 to the negative 31 kg, what you can do is that you can calculate the force. All right, so you can calculate the force acting. All right, so you know the mass, we have the force, we can calculate the acceleration. That's what I wanted to say. So we can calculate the acceleration of this electron. Since we know the mass of the electron, that's a constant number that we'll always get. And since we know the force F. So acceleration is just the resultant force over the mass. And of course, you'll get some acceleration here. So it's going to be 1.6 times 10 to the negative 14 divided by 9.11 times 10 to the negative 31. All right, so work that and tell me what you get. You should get some number to the 15 or the 16. So it's a very, very fast acceleration. All right, so that's the concept. So when charges are in magnetic fields, what will happen is that there will be a force acting on the charges. All right, so what I want you to do is to punch that in the calculator because you'll be using these small numbers and in the exam. So punch that in the calculator and tell me what you will get. All right, so I am going to, there are some recordings from last time that I'm going to be sending to you as well. All right, so as soon as you have an answer, you can let me know.
Sir, I don't know if this is right, but 1.756 times 10 to the 11th.
Times 10 to the 11. All right, so let me think of a calculator finally. That's 1.6 times 10.
Yeah, that should be right. That should be right. Sorry.
Okay, 10 to the negative 14. And that will be divided by 9.11 times 10 to the negative 31. And you should get, so you get 1.756 times 10 to the negative times 10 to the positive 15.
Positive.
Yeah, that's correct.
Oh, 15. All right.
Yeah. All right, so that's for that. So you work with small numbers a lot, especially in module 3. All right, so that's ideal. So when charges are moving in a magnetic field, it experiences a force. And so we're on the same idea, right? So this is the same general idea, but this time that is going to cause something known as the Hall effect. All right, so this diagram, let me explain what is happening in this diagram. This is what we call a rectangular cylinder, rectangular conductor. So it's a box. All right, so what I'm going to do is to remove. All right, so let the charges stay for now. So this is a box, and of course the X's represent magnetic field that is going into the board. And so what's going to happen now is this. All right, so let's remove the charges, because when you switch on the current, the charges are going to come on the sides of the conductor. And that's what we call the Hall voltage. And the reason for that is because when charges are moving in a magnetic field, it experiences a force. So the charges accumulate on the sides of the conductor, all right, as is going to be shown. So inside the conductor, you have a negative electron, and that negative electron has a velocity v, as shown in the diagram, in the arrow. All right, if we apply Fleming's left-hand rule, the magnetic field is X, and it's pointing in to the board. Conventional current is flowing opposite to current electron flow. So that's indicated by this green arrow and the I. So my middle finger will be pointing in the direction of conventional current I. My first finger, my pointing finger, will be pointing in the direction of the magnetic field. So my thumb will be pointing downwards using Fleming's left-hand rule. So when I use Fleming's left-hand rule, there is a charge. The charge is moving inside this conductor, which is still space. It's in a magnetic field, so it will experience a force. It will experience a magnetic force. So what happens now is that all of the electrons will have a force acting on it downwards. So you're going to have an accumulation of negative charges on this side. All right, so all of the atoms are being stripped of their electrons, and the electrons are accumulating here. So once electrons are accumulating on the downward face, where the electrons are coming from is going to obtain a positive charge. All right, so that's ideal. So up here, you have a deficit of electrons, which is going to be my accumulation of positive charges. Down here, you have the accumulation of the negative charges. When you have positive like this and negative, if you should take a wire, you will record a voltage. All right, so that's the concept. So if you take a wire, you will record a voltage. And that is what the Hall effect is. So in words, the Hall effect is when a conducting wire is placed in a magnetic field, what you're going to register is a voltage on the side of that conductor. All right, and that voltage is called a Hall voltage. All right, and so we have a nice formula for the Hall voltage. VH is equal to BI over net, NET. And I think I defined all of these variables on the other side. But VH is Hall voltage, B is magnetic flux density, I is the current flowing in the wire, N is the number of charge carriers in the wire, E is a charge on one electron, and T, that's the thickness of the conductor. So the Hall voltage, all right, depends on the magnetic flux density, all right, I, the current flowing, the number of charges, the number of electrons as well, and the thickness of the conductor. So that is what the Hall voltage is. So this is still based on Fleming's left-hand rule, and it's still the same concept as a charge moving in a magnetic field. When charges are moving in a magnetic field, they experience a force. And because these forces are acting on these electrons now, it's going to force them to accumulate down here on this face, leaving positive charges on the opposite face. Once you have separation of charges like that, you know that you will have a voltage, just like a battery, right? So the reason why a battery has voltage is because there's a positive terminal and a negative terminal. That tells me that I have voltage. When we did capacitors, the same argument, all right? This side of the capacitor is positive, next side is positive, negative. There's a voltage across the capacitor as well. So once we observe this, we know that we have a voltage. All right, so that's the concept. And of course, the force acting on the electron is calculated by this very formula, F equal BQV sine theta. All right, so we'll know the velocity of the electron. We know the magnetic flux density that the wire is in and is acting on the electrons. And of course, we know the charge on one electron. So we know B, we know Q, and we know V. And of course, we know the angle theta. All right, so we can calculate that force as well. All right, so this voltage set up on the side of the conductor is called VH, where VH is the Hall voltage. All right, so that's the concept. All right, so as soon as you finish the screen, just let me know. We'll just move again. All right, and of course, I will also send this to you in terms of the slides, as well as the recording as well. All right, so you can have a second glance at it as well.
Yes,
right?
sir. Finish.
So this is the Hall effect. So for the Hall effect, as I was talking about just now, the formula is on the other page. So VH is VI over NET. So VH equals VI over net. All right, easy to remember the word net. So VH is Hall voltage. All right, so VH is Hall voltage. All right, so VH is Hall voltage. V is magnetic flux density Tesla. I stands for the current in amps, and N is the number of charge carriers. All right, so that's the concept. So if we want to calculate, all right, so 1 second, let me get rid of it. Okay. Yeah, so if we want to calculate, VH equal BI over NET. All right, so that's the concept. All right, so this is the example that we had on the other side as well, where you have the magnetic field is in red going into the board, and of course we have the downward forces on the electron. So this is a very, very important concept because you have some voltmeters that are now designed based on the Hall voltage. All right, so that's ideal. So you have voltmeters designed like this, and Hall probes are also designed based on this formula. So here you have voltage is directly proportional to the magnetic field. All right, so you have some devices that is used to measure magnetic flux density, and it is, sorry, excuse me, it's based on this principle. VH is directly proportional to B, magnetic flux density. So as the magnetic flux density increases, the voltage, right, this voltage VH will also increase. So if we have an instrument that can measure voltage, we have an instrument that's also measuring magnetic flux density as well. All right, so that is what this formula is telling us. So once we have an instrument that's measuring the voltage, technically we're measuring how strong the magnetic flux density is. All right, so that's the concept. So VH, direct proportional to B. And this is a principle that we use to make a Hall probe. A Hall probe is a device that is used to measure magnetic flux density. So it's a measuring instrument, just like a voltmeter. All right, so voltmeters are used to measure voltages, and meters, current. So Hall probe is used to measure magnetic flux density, and it's based on this formula, VH equal BI over NET. All right, so that's the idea. All right, so I think I have some examples about the place. Let's just continue. All right, so a quick little exercise of the formula. So in this question, so I just extract the information. So you have a conducting wire, all right, that's placed in a magnetic field of 1 Teslas. The number of charge carriers is 10 to the 29 per meters cube. So that is the number of charges in this space. Remember, per meter cube is volume. The charge on the electrons moving in the conductor is 1.6 times 10 to the negative 19 coulombs. Of course, electrons are negatively charged. And of course, the conducting wire is carrying a current of 10 amps. If the thickness of the wire is 1 times 10 to the negative 3 meters, we would want to calculate the Hall voltage. So we know that there will be a voltage on the side of the wire because each of the electrons in the wire is going to experience a force. So when the electrons experience a force, they're going to accumulate on one side of the wire. And then now you're going to have positive charges accumulate on the opposite face of the wire. This charge separation is what the all voltage is. So in order to calculate this, VH is equal to BI divided by NET. All right, so you can make that calculation for me. So we know what B is, we know what I is, we know what N is, we know what E is, and we know what T is. But secondly, for a semiconductor, so we're going to be talking about semiconductor very, very shortly. For a semiconductor, what we notice is that the magnetic flux density being the same, the number of charge carriers is a little bit less, much, much less, 10 to the 4 less. The thickness is the same current, but what you will notice is that there will be a difference. So what we're saying here is that if the number of charge carriers were to change, your all voltage will also change. So here VH is inversely proportional to the number of charge carriers. So what I wanted to do is to perform the calculation for the top one, all right, using this information. All right, so this is for a regular conductor, and then we're going to perform the same calculation for a semiconductor. When we do that, we can see that there will be a difference in the voltages that is set up at the size of the wire. So as the number of charge carriers increases, you're going to register a much, much, much smaller Hall voltage. But if you increase the number of charge carriers, if you decrease the charge carriers, so if N decreases, your Hall voltage will increase. So right here is inverse proportionality. So if N decreases, VH increases. And if N increases, then I know that the VH has to decrease. All right? But this is a very important property of semiconductors. So you can set up a nice voltage because of the value of N. The value of N is smaller, much smaller than that of conductors. And of course, we'll explore this in great, great details, semiconductors. All right, so what I want to do is just to take a minute or two, perform this calculation, and then we'll move again. All right, so you're calculating the Hall voltage for a conducting wire in part one, and you're calculating the Hall voltage for a semiconductor in part two, where all of the information is given.
Sir, 6.25 times 10 to the minus 7.
All right, so that's for the first one.
Yeah, I think so.
All right, cool. Have a go at the second one.
I haven't done that one yet.
Yeah.
6.25 times 10 to the negative 3.
All right. All right. So what you should see in your answer is that VH for the conductor should be smaller.
Smaller on the second, on the first one
Okay.
in the conductor than the semiconductor.
Yeah. All right. So based on the relationship, that VH is proportional to 1 upon N. All right, so that's for all right, so VH, VI over NET. All right, so that's no sweat. So let's move again. So that's the Hall effect. All right, so next we're going to talk about the force between two current carrying wires. When you have two wires side by side as shown in these diagrams, two wires carrying current side by side like this. In this wire, you have a current I1 flowing. In this wire, you have a current I2 flowing. There is going to be a force on the wire. The force can either be attractive or repulsive. Now, when the currents are pointing in the same direction, you're going to have attraction. All right, so when the currents are pointing in the same direction, then the two wires will be attracted to each other. So if I have a wire carrying a current I1 and a next wire carrying a current I2, there's going to be a force of attraction between the two wires because the two currents are pointing in the same direction. All right. Next, if I have a next wire, next system, all I do is just change the direction of the current in one of the wires. When the currents are flowing in opposite directions, as shown here, then the two wires will want to move apart, and that's repulsion. All right, so that's the first thing first. So same thing, is just that the currents are moving in the same direction in this example. Currents are moving in opposite direction in this one. All right, the same formula applies for both. It's just that in one, when the current is pointing in the same direction, it's attraction. When the currents are pointing in opposite direction, it is repulsion. All right, so that's the concept. We can calculate the magnitude of this force. All right, using this formula, F is equal to mu naught times I1, I2, all divided by 2 pi r multiplied by the length L. All right, so that's the concept. All right, so that's the ideal. So once we know the current in both wires, the distance between the two wires, which is R, and the length of the wires, we can calculate. All right, we can calculate the force. So F is equal to mu naught times I1 times I2 times L, all divided by 2 pi r. So your F stands for force, measured in newtons. Mu naught needs no introduction. It's just the constant that you will always get, the permeability of free space. So it's 4 pi times 10 to the negative 7 Henry per meter. I1 and I2, these are the currents flowing in the wire. L is the length, and R is the distance. All right, so that's the concept. All right, so that's ideal. So once I have the current in the wires, the distance between the wires, and the length of one of the wires, I can calculate the force, all right, that's acting on the wires. So when you have two wires that is carrying a current and they are placed side by side like this, there is going to be a force acting on each of the wires. All right, so that's the concept. All right, and again, this is still based on Fleming's left-hand rule. We're not doing anything different. All right, so that's the concept. So we can actually prove this as well using Fleming's left-hand rule. As before, we use the grip rule to predict the direction of the magnetic field. And once a current is moving in the presence of a magnetic field, then we use Fleming's left-hand rule to predict the direction of the force. So that's what they did. And it shows that when the currents are pointing in the same direction, that's attraction. The currents are pointing in opposite direction, that's repulsion. All right, so that's the concept. All right, so F equal mu naught I1 times I2 times L, all divided by 2 pi R. Of course, all of these variables are defined. All right, so there should be an example about the place. So I'll send you both the recording and the slide so we can just continue. All right, so think of an example where you use that formula just to make a calculation. All right, so this is for this. So in this question, you have a wire X and a wire Y. In X, you have a current of 2 amps. In Y, you have a current of 3 amps. All right, so that's the first thing first. All right, so you have a current of 3 amps flowing in the wire Y. Since the currents are pointing in opposite directions, so we know that there is going to be a force of repulsion between the wires from theory. What they wanted us to do, they want us to calculate the magnetic field, all right, due to the wire X. All right, so they wanted us to calculate the magnetic field due to the wire X. All right, so when a current is flowing through this wire X, as we have seen before, so nothing new because we did this already. When we have one wire and it's carrying a current at a certain distance away from the wire, you're going to have this formula to calculate the magnetic flux density. All right, so Bx is mu naught, the current flowing through this wire X, because we want to calculate the magnetic flux density due to this wire X. So Bx is equal to mu naught I1 over 2 pi R. All right, so where we know mu naught, we know the current I1. The distance between the wire is known as 0.01 meters. And the length of the wire is 0.05 given as well. So I can calculate the magnetic flux density due to the wire X. If I want, I can calculate the magnetic flux density due to the wire Y, all right, as well. All right, so that's ideal. So first, they ask us to calculate. First, they ask us to draw how the forces will be acting on the wires. So since the currents are pointing in opposite directions, the forces are acting like this. That's repulsion. Part 2, we can calculate the magnetic flux density due to the wire X. All right, and that is using this formula, mu naught I over 2 pi R. But because we're talking about the wire X and the current X1 is flowing, all right, sorry, the current I1 is flowing through X, we use this formula. For part 2, we can calculate the force between the 2 wires. All right, we can calculate the force between the 2 wires. F equal mu naught I1 times I2 times L all over 2 pi R. So I know the current in the first wire, I know the current in the second wire, and I know the length. And you're going to use the length of this small wire because the magnetic field from this wire extends from here to here, right? Where you see I have the dotted line. Since there is no current flowing here, then there is no magnetic field acting on X in this region, no magnetic field acting on X in this region due to the wire Y. So the length of the conductor that you will use is the length of this shorter wire. So to calculate the force, F equal mu naught I1 times I2 times L all over 2 pi R. All right, so that's what I wanted to do. So I wanted to just crunch numbers. So what I did was to draw the diagram, and extract the information. So the distance between the two wires here is R. All right, so R is the distance between the two wires. The length of the shortest wire is 0.05 meters. The current flowing in the wire X is shown here. The current flowing in Y is shown. And the constant is also given. Mu naught equal 4 pi times 10 to the negative 7 as well. So you can calculate the magnetic flux density due to the wire X. And for part 3, for practice, I'm going to ask you to calculate dy. This is the magnetic flux density